Here in this video, we're taking the limits of sequences. This is the more important video. Of course, if you don't understand what a sequence is, you can't do anything. But this is the one. But okay, let's just get to it. All right. So when we take the limit of sequence, it's basically we're going to do the function version, the regular function version, the non-discrete version, the continuous version, right? And if that has a limit, then the sequence, the discrete version of the function, has a limit. Okay, so essentially they're basically the same thing. All right, so here is a typical sequence. Change it to the functional version where it's not discrete but continuous, well, relatively continuous, right? Because this is going to work from n is greater than 1, so this is going to be x is greater than or equal to 1, right? So -1 is not part of the domain here. And we take the limit as x goes to infinity of f of x, and we get 1, right? Remember the rule, and look at the coefficients if the degrees are the same, so the limit is 1. Since the limit of this function is 1, then the limit of the sequence is 1. And we say it converges to 1. We say that the sequence converges to 1. All right, so this is another example. All we're going to do is take the limit as x approaches infinity. This was covered in chapter 5. This was chapter 5. And the limit of that function is e. And if the limit of that function is e, then the limit of the sequence is e. That's all that is. Okay. Now these properties of limits are not new to you. You've seen this before. This was applied to functions before, and what this theorem says is that it also applies to sequences. Right? If you have two different sequences and each of them have a limit, and you can add them. If you add the sequences, you can add the limits. If you subtract the sequences, you can subtract the limits. Same with multiplication. Same with division, as long as the denominator sequence, the limit is not 0. All right. Okay. So here, looking at this example, we're going to determine whether this sequence converges or diverges. This sequence alternates between 2 and 4. This was in the previous video. Okay. And it goes back and forth between 2 and 4. So the limit does not exist. If the limit does not exist, then we say the sequence diverges. That's it. Right? The limit doesn't exist because it hops back and forth between 2 and 4. B, right? We take the limit of the functional version. And by the way, this is being nitpicky, but as a presentation, I have to be the more nitpicky. But if you just take the limit in the sequence version, I am perfectly okay with that, right? The logic is basically the same. The limit is -1/2. So this sequence converges to -1/2. Right? So it is identical. The only difference is the letter we use. And the implication here in the limit, they're saying x is everything, right? All real numbers. And here, n is positive integers. But, essentially it's the same thing. Okay. In this example, we will end up using L'Hopital's rule to determine convergence. All right, so here we're going to use basic functional notation. Take the limit as x goes to infinity. By the way, all of these are going to infinity, right? When we talk about a sequence conversion, diversion, we're looking at the sequence as it goes to infinity. All right, so there's no like as x goes to 3 or anything like that. And we have the infinity over infinity version right now, right? As x goes to infinity, x squared goes to infinity. As x goes to infinity, 2 to the x minus 1 goes to infinity. We apply L'Hopital's rule, and we still have infinity over infinity. So we apply L'Hopital's rule again, and this time the numerator becomes 2, and the denominator you just have another factor of natural log of 2. So what is happening here? This goes to 0. Okay, so that means the sequences are going towards 0. So the sequence converges to 0. Okay, that's it. All right, squeeze theorem. So squeeze theorem is going to be useful soon. It's actually not so useful here. Generally, it's easier to do things other way, but we'll go ahead and look at this one. All right, so this is the first time you've seen a sequence that looks like this. You will see more of the factorial as we progress into series. All right, so this is 1 over n factorial. Remember, n factorial, let's say if it was 5 factorial, it would be 5 times 4 times 3 times 2 times 1. Okay. All right. So let's look at this. Now we know that a sub n negative 1 over 2n converges to 0. Okay. If you let n go to infinity, this fraction goes to 0. It kind of hops back and forth between negative and positive, but it goes towards 0. All right. And we also know the positive version converges to 0. But why these sequences? All right, so we're going to compare n factorial to 2 to the n. Right? So this is n factorial, going from 1, 2, 3, blah, 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 up until n. And this is 2 to the n, so there's n 2's. Right? So this 24 is 1 times 2 times 3 times 4. Okay, so this is the first 4 terms multiplied together. And here, this is 2 to the 4th power. Okay, now why do we go up to 4? Well, the point here is that starting from here, n factorial is bigger than 2 to the n. N factorial is bigger than 2 to the n. See, at n equals 1, 2 to the n is bigger than n factorial. At n equals 2, this is 4, and n factorial is 2. And then 8, then 6, and then, so that's what we're looking at here. So we're looking at when does n factorial become bigger than 2 to the n. And then here, this is n minus 4 factorials. So we've taken in the first 4, right? And here, there's n minus 4 factors here. So the comparison we're looking at only works beyond n equals 4. All right. So whenever n is greater than or equal to 4, the n factorial is greater than 2 to the n. So we're going to put that restriction in there. For n greater than or equal to 4, 2 to the n is less than n factorial. Now, why do we care about it being less than n factorial? Because if we take the reciprocal, we're flipping it. Remember, whenever we take the reciprocal of an inequality, the inequality changes directions. So 2 to the n, if I flip it, take the reciprocal, makes it 1 over 2 to the n, and take n factorial and find the reciprocal, I get 1 over n factorial. The less than becomes a greater than. All right, now, so that means this version, the negative 1 to the n version of this 1 over n factorial is going to be, if it's 1 over n factorial is less than, so it's going to be less than 1 over 2 to the n, the positive version. But then it would be greater than the negative version. Okay, and remember we just chose this earlier? This was like a sub n, maybe this was a sub n, and b sub n, right? And remember, a sub n went to 0, and b sub n went to 0. Then by the squeeze theorem, that's going to go to 0 because these 1 over 2 to the n, and negative 1 over 2 to the n, they're, oh, that's written incorrectly. That's not 2n, it should be 2 to the n. All right, that's going to 0. All right, so since those are going to 0, then the one in between must go to 0. Not hard to imagine. Okay, absolute value theorem. Basically, this says if the absolute value of the sequence is going to 0, then the non-absolute value is going to go to 0, which kind of makes sense. This term is a kind of a background for things yet to come. I'm not going to really use this much, okay, until later on. This whole idea of taking the absolute value. Alright, so here, all we're doing is finding the nth term of a sequence. We're not going to do much of this. So you look for a pattern. This is 2, 4, so it's multiplied by 2 every time. The denominator is odd numbers. Well, actually, the takeaway from this example is not finding the nth term. The takeaway should be, how do I figure out an odd number? What is a generic form of an odd number? So this 2 to the n minus 1 is a generic form of an odd number. All right, what does that mean? Well, you're going to have to come up with a formula for what an odd number looks like. This is not the only version. Like 2 to the n minus 1 is one version. 2 to the n plus 1 is another version. Okay, so it kind of depends on what you want to start with. So if this started with 3, then 2 to the n plus 1 would be the better choice. Right? That'd be 3, 5, 7, okay? So as long as you're adding or subtracting an odd number from 2n, then this expression becomes an odd number. Right? Numerator was pretty easy. Right. But then what we're going to do is look at whether this converges or diverges. So we take the limit as x goes to infinity. And we get this. Well, this has infinity over infinity, so we do L'Hopital's rule. When we take L'Hopital's rule, and I should have LHR here, and I neglected to put that there. All right, so you get this, and as x goes to infinity, this is going to infinity. So that is not going to converge, it's going to diverge. The sequence diverges. Alright, so this was a video on limits of sequences. Okay, and in the next video we're going to talk about bounding and or whether a sequence is monotonic. Okay, that's it. Bye.